Welcome to the short discussion on the topic shear force diagrams and bending moment diagrams for simple beams, and this is a part of the syllabus in the unit shear force and bending moment, right, in the course strength of materials 1. So at the end of this particular discussion, I am hoping that you will be able to construct or draw the shear force and bending moment diagrams for the simple beams which are subjected to point loads as well as couples, also distributed and varying loads. Okay, particularly this particular construction of the shear force and bending moment diagrams, I am using the concept of relationship between the loading, shear, and bending moment. Okay, there was a topic which I had discussed on the relationship between in one of my previous discussion. It was there about the relation between the load and shear and bending moment. There is also another way to construct the bending moment and shear force diagram, which is called method of sections, that I have discussed in the some other session, right? Now let us look at the just review what are the uh, uh, main points of that relationship between the load and shear and bending moment. So for establishing the relation between the shear as well as load as well as bending moment and shear force, we have considered and simply supported beam with which is subjected to uniformly distributed load. So the outcomes of that particular discussion are listed here. So the relation between the shear force and bending moment is like this. The rate of change of bending moment at a particular section is equal to shear force at that particular section. Or another way of saying is, if I have selected two different points, right? If I have selected two different points, say 1 and 2, right? And if I want to know the bending moment change between those 2 points, let's say m2 minus m1. I have selected 2 points on the two cross sections, you can say, on a beam, and of course we know that the bending moment will keep changing from point to point. So if I selected point number 1 and point number 2, if I want to know change between those moment values between those two sections, I could simply find the area of the shear force diagram between those 2 points, say 1 and 2. This is one outcome of the concept of relationship between the bending moment and shear force. Similarly, I will also get another relation between the shear force and loading. That relation says the rate of change of shear force is nothing but the intensity of the loading. Okay, so if you want to know, if you select the same way, select two different sections. If I want to know the shear change between those 2 points, say V2 minus V1, if I want to know this, I can simply find the area of the given loading diagram, say between those 2 points, say 1 and 2, W times dx. This is the another relation that we can derive from that concept of relationship among these three quantities. Okay. As far as the shape is concerned, your loading diagram on the simple beam or even cantilever beam decides the shape of the shear force as well as bending moment diagram. For example, if your loading is distributed load, uniformly distributed load, your shear force variation diagram will be varied in a linear fashion, whereas your bending moment diagram will varies in a quadratic fashion. If you are taking a point load, shear force varies constantly, and bending moment diagram varies linearly. If you are taking a varying load, uniformly varying load, shear force varies in a second order, quadratic, and cubic. The bending moment diagram is varying in a cubic fashion. Of course, when there is couple, your shear force diagram will not be influenced by that, whereas bending moment diagram will be a constant variation, maybe having some kind of jump at the point of moment, either upwards or downwards. Okay. What was this exercise is telling about is, with the kind of this relationship, we can directly, without even knowing the magnitude, you can sketch the shape itself. Straight away you can sketch the shape just by knowing this relationship between the load and shear force and bending moment. You can draw it. You may not draw the exact coordinates that we have to do by finding these areas of the loading diagram as well as the shear force diagram, but as far as the shape is concerned, we can straight away flat it approximately, right? Now, this point, this already I have told, the area of the shear diagram will give the bending moment at particular section. And depending upon the shape of whether the shear force diagram is increasing or decreasing between two segments or two cross sections, the bending moment diagram may be, it may be a concave shape, or it may be concave up, or it can be convex down, which is also called convex shape. Okay, these points are the outcomes of that particular relationship. Now let us see how this particular outcome will be using to construct all basic loads. For all basic, using this particular relationship, for all basic loads I can construct the no shear force and bending moment diagram. Let us see how we can do that. So for the construction of the bending moment diagram, first step requirement is calculation of the support reactions, right? This I have discussed during the discussion on the simply supported beam reactions, right? So there was a topic which I have covered in the previous sessions about the evaluation of the support reactions in simple beams, right? We can refer to that, but as well as, because here the loads considered are simple, we don't have to endeavor much. We can straight away put this simple. For example, here is a concentrated load acting at the center, so it is easy for me to, with common sense I can put these reactions are, say, W by 2 and W by 2. But in case of difficulty, for example, you have a complex loading phenomena where you cannot offer to straight away write the reactions, then as usual, as we discussed in that topic, you can simply use the equilibrium equations, namely sigma Fy equals 0 and sigma Mz equals 0. At any Mz you can apply at the any one of the point or any one of the support, Mz equal. These two equations will give you the support reactions. Because in cantilever beams, you don't have to find the reaction. You can straight away start the shear force bending moment diagram using this concept of shear force and bending moment relationships. Okay, but in simply supported beam, the advantage in cantilever beams, there is a free end. You don't have to find reaction. You can start the construction of the SFD and BMD from the free end, but here it is not possible. Both ends there are supports, so without finding the support reaction you cannot proceed for the shear force and bending moment diagram. Okay, so assuming that you are I am assuming that you are all ready with the support reactions, you are able to find. In case of not able to find, please kindly refer to that particular discussion. You will be able to find out the support reactions for simply supported beam for all kinds of loading, right? Now let's start. Assuming that you got a reactions, let us start. So first thing you have to note here is, we have to follow sign convention. The positive sign convention here is, for a shear force, here whether you are proceeding, the way you proceed, that determines whether you are on the left of the section or right of the section. When you are moving from left to right, that means your section is on right side to you and you are on the left of the section. You can say, when the section is right side to you, right, you are on the left of the section. So when they are on the left of the section, the upward forces you have to take positive and the downward forces as negative. Okay, similarly bending moment, clockwise moments are negative when you are on the left of the section. and vice versa. When you are on the right of the section, downwards are negative, upwards are positive. Okay, and your as far as bending moment is concerned, anti-clockwise moments are negative, and on both what do you call anti-clockwise moments, you know, when you are on the right of the section, the anti-clockwise moments are taken negative. On the anti-clockwise moments are taken negative. Okay. Similarly, on the right of the section, right, your moment here, you are on the, sorry, I think in my flow, see, just look at this. First one, when you are on the left of the section, positive set I am telling, when you are on the left of the section, that means there is section is here. For example, in this case, you take a section here, that means you are here, on the left of the section. The movement, sir, what type of movement it is? It is for you, no, for this particular section, this is going to be a clockwise movement. This is to be treated as positive. Okay. Similarly, when the moment is acting right side of you, and if it is in the anti-clockwise direction, then also that is positive. Okay, that point you have to observe. Similarly, if this is the section, for the when you when this is the section, for you are on the left of the section, and your movement is say anti-clockwise, this is negative. Similarly, when this is your section, you are on the right of the section, and your movement is in the clockwise direction, this is to be taken negative. I hope you understood now. Let's, with this understanding, let us start. Mostly, no, we will be taking section, no, where we will be moving from left to right, and section is usually on your right side. That means you are on the left of the section. Okay. So let us start now. So we got the reactions now. So here for the shear force diagram, what we will do is, we will take simply the area of the, if you want to construct the shear force diagram, you can, if it is UDL or UVL, you can find the areas. But when it is a point load type, you can, you know, cumulatively add it one load after the other. For example, here whenever you want to draw shear force and bending, minimum you consider 3 number of points, right? So let us take one point here. So where to take? You can take at the both ends and one at the middle. So let's say 3 points I have considered. So point number 1, point number 2, and point number 3. Okay. So if I want to get the shear force at the point 1, okay, it is nothing but whatever the forces are no, acting here, you just take those forces. For example, reaction here is W by the shear force is nothing but no, the forces algebraic sum of the vertical forces. So this is a vertical force. So the shear force here will be simply W by 2, right? But W by 2 acting upwards or downwards, it is acting upwards. So when you are on the left of the section, upwards is positive. So on upside you can draw a value of W by 2. Okay, let us write this one here. Okay, then you can continue, because in between there are no other loads. You can continue this up to the point 2. Alright, so you continue that particular whatever ordinate you are getting up to the point 2. Okay, now after reaching this point, there is a downward force acting. We are moving from left to right. So when you are moving from left to right, your W is going to be minus W, right? So already plus W2 by W by 2 is there, and this becomes minus W. So you are going to get now summation algebraic sum as minus W by 2. So here you got an ordinate of, here it is W by 2, right? This ordinate is plus, and the value is W by 2. Okay, then you got another ordinate here, that is also W by 2, but it is minus. So you can write that now. Okay, this is another ordinate. Okay, you can make it straight actually. Alright, so this is your minus W by 2. That's all. That is the shear force diagram. Okay, so what we have done, we just taken whatever the vertical forces acting, keep adding one after the other, right? Because it's a point load, you don't have to find any areas you can of the loading diagram, you can find only when there is UDL and UVL. Okay, so now you can simply add the ordinates. So here is a support reaction W by 2, which is a vertical component, and then proceed with that, no other loads are there. And then when you reach W, because W is acting downwards, you are moving from left to right, therefore this becomes minus and the ordinate becomes minus W by 2. Then comes to the bending moment diagram. Here also you select 3 points, say 1, 2 and 3. 3 points you are selected. So now for this, as we told earlier, if you want bending moment diagram, you can simply find the areas of the shear force diagram, right? So what is the area of this diagram? Here what is the ordinate? First of all, here the ordinate is at the simple supports, roller support, hinged or pinned support, they don't carry any moment. So you can safely put a bending moment at the both ends as 0. This is the first understanding whenever you want to draw the bending moment diagram for a simple supports, the ordinates at the ends going to be 0. Then if you find one more point, finish your diagram is over. So how to find that? You can find that if I want to know the, here it is 0, here it is some value, say this is your m2, this is your m1. We told m2 minus m1, if you want to get, you find the area of this. So what is the area of this diagram? W by 2 is a rectangle, right? W by 2 times what is the distance over which it is acting? L by 2. So ordinate will be, your ordinate will be WL by 4. So you got it now. This ordinate is WL by 4. Okay. Now you can join the 3 points. But how to join? I told you already. When there is a point load, the variation of the bending moment diagram will be linear. So join all the 3 points with a linear line. So you can join to here and here to here. Right? Is a 0 ordinate. That's all. So this is going to be our bending moment diagram. Alright. So now let us move on to the another type of loading. Next loading, let us select the, so this is the diagram to the scale, right? W by 2, this is what we have done. W by 2 and then downwards W by 2, right? And this is the bending moment 0 at both ends, and there is a value of WL by 4. Alright. Now let's move to the another loading, namely uniformly distributed load. Right? Here also same concept. You should first find the support reactions. So I am assuming that you know the support reaction. It is very easy actually. Is a symmetric loading having a total load of WL. So will be W times L is the total load, right? That coming from UDL. So share it to both supports equally. That means WL by 2 for this, WL by 2 this, and totally it is WL, right? So support reactions are over. Now you follow the sign convention as I told you earlier. When you are on the left of the section, upward forces are positive. When you are on the right of the section, downwards forces are also positive. Right? Similarly, when your movement, as far as movement is concerned, left of the section, clockwise movements are positive. Right of the section, clockwise movements are positive. Whereas coming to the moment, left side downward force, left side, coming to the shear force on the right of the section. Right, on the left of the section downwards is positive, negative, and on the right of the section upwards, kind of vertical forces or shear forces are also negative. Coming to the moment, also when you are on the left of the section, anti-clockwise is negative. When you are on the right of the section, clockwise is negative. Right? So following the sign convention, you can start constructing the shear force and bending moment diagram. Here the type of the load is UDL. So you can simply find the area of the what do you call the diagram, the loading diagram, right? So I am starting now. So 3 points are selected, one at the end, another at the middle, another at the other end. So 3 points I have selected. Say you can call it as 1, 2, 3 as you like. Okay, and then let us start drawing the shear force and bending diagram, construction of the shear force diagram. So this is our third point, let's say. So after taking this, now start drawing this. Now if you want to find the ordinate here, okay, the ordinate is already available. Before that, whatever loads, vertical components are there, you add it. Before that, nothing is there except this. At this location, the shear force is WL by 2. So you draw an ordinate of WL by 2 at this location. Alright. So you are drawn that WL by 2 ordinate. Keep it. So this is plus, right? Left of the section you are, and the force is acting upwards, so it's going to be WL by 2. So let's keep that as it is and then move forward. This is WL by 2 for me. Okay, let's go for the next one. The ordinate here, right? So as you are proceeding, right? So what happens here? WL by 2, right here, and then this load is also coming now. As so far we have only one load. As we move here, WL by 2 is there, right? So here what we have to do is, whenever you are drawing shear force or bending moment diagram, any load other than point load, for example UDL or UVL, you should convert them into a point load. This is compulsory requirement. So if I convert this particular loading into a point load at the center, so let us I am going to take only up to the center. So up to the center, this particular load, when you convert it into this UDL converted into a point load, what happens? It becomes WL by 2, because acting over a distance of L by 2, this load becomes WL by 2, a point load acting at exactly at the center of that particular distance. That means this is L by 4, this is also L by 4, right? So what happens now, once you have converted this particular no, what you call this, what we no, load, we call it as WL by 2, right? So this particular one, as we were moving, right, this way, slowly this particular one becomes, when we consider the load up to here, right, then it is becoming WL by 2, right? Or another way of saying this is, uh, if your load is acting at a distance, say x, instead of directly taking L by 2, let's take at a distance x. Then what happens? Your shear force at the particular distance becomes W times x, but it is a negative sign, because when you are moving from left to right, downward is taken negative. Now for this you add your WL by 2, because WL by 2 is there from the beginning, so you add that value. So Wx plus WL by 2. Right? Now in this you keep substituting. If you want to know the ordinate at any point, let us say if you want to find at L by 2, put x equal to L by 2. Then what it happens? The whole equation becomes W minus W times L by 2 plus WL by 2. That means 0. Here it is 0. The ordinate is 0. Next, if because the load is uniform till the end, so you can, this particular equation can be valid till the end also, right? So if I put x equal to L, so it becomes minus WL plus WL by 2, right? So that is minus WL by 2. That means the ordinate is negative and goes down. So this is also minus WL by 2. This ordinate is going to be minus WL by 2. Say this is minus, can write minus WL by 2. Alright. So now join all three. That's it. That is your shear force diagram. But how to join, whether it is a straight line or a curved line or which line? So we already told, when there is, just in the before table I told, right, when there is a UDL, your shear force is going to be a linear variation. So now you can use that particular uh, relationship. So I have to join by linear line all the 3 points. So here is WL by 2, first join to 0, again is a linear line, and then again join to this particular one, finish. That is your shear force diagram. This is your SFD. Alright, next one is your bending moment diagram. Okay, so here when you are trying to construct the bending moment diagram, you just follow the area of the shear force diagram. That's what we told. We don't have to again come from the load. So to find that, always remember, at simple support, at roller support, the bending moment is always 0. So 2 points you know by default, 0 here, 0 here. Then after all, if you know this point, your bending moment is completed. Okay, this ordinate only I have to know, central ordinate. So how to get that? As I mentioned previously, if you find the area of this particular diagram between 1 and 2, you can get the difference between the ordinates is already 0. So this ordinate you will be straight away getting. So what is the area of this diagram? This is in the form of a triangle. So half times base times height. This distance is L by 2, right? So that means half into W L by 2 into L by 2. That becomes WL square by 8. Okay, so the ordinate here is WL square by 8. Okay, WL square by 8. Over. So you have to join the 3 ordinates. But again, the relationship you have to use when there is UDL. Load is UDL. Your variation of the bending moment is second order quadratic equation. So use the quadratic curve to join it. That's all. Okay, to be exactly drawn to the scale, it look like this. WL square by 8, and this is a linear curve, WL varying from minus plus WL by 2 to minus WL by 2, and it is 0 at L by 2. Okay. Next kind of loading is the couple. Here so as we told, the support reaction you have to find. So because it is a anti-clockwise couple, your reactions will be forming a clockwise couple. That means this is plus M by L going upwards, and this is minus M by L other side. This is going to be a downward reaction, and M by L. Okay. So your first step is over. That is construction of the what you call finding of the support reaction. This is essential. So I am not in detail discussing. As I told you, you can refer to that previous section of finding the support reactions, whether cantilever beams or simply supported beam. Simply using the equilibrium equations, two equilibrium equations, sigma mz equal to 0 and sigma fy equal to 0. Okay. Now construction of the bending moment diagram for couple. As we told earlier, when the couple is available, if it is a cantilever beam, of course it will not have, it will be not having any effect on the shear force diagram because of the couples. Okay, but if you are having a kind of a couple here, right, in a simple beam, so the shear force diagram will be a constant one. Let's see how to do that. So M by L is the value here. So when you are drawing shear force diagram, you just look at the forces, anything that are on the left of them, because you are moving from left to right. Before that, nothing is there. So first load is your first input for shear force diagram, that is M by L. Okay, now let us keep that. There is one point. Second point you take at middle, and third point you take at the end. As we told, 3 points we are taking, right? So this is, let's say third point is at this end. Okay. Now m by l plus you got. Why plus? Because the sign convention says that the left of the, when you are starting from left to right, upward reactions you should take it as positive. Okay. So this is your m by l, you got first value, right? Then move forward because nothing else is, no load is there in between, so straight go up to your middle point till m comes. So when you enter this point, this will have any effect on the bending moment? It is not a load, it is a bending moment, so no uh, effect of this particular loading, right? Now after moving this, going forward, so you can take this straight till the end. That's it. Here also m by l. You can check it always. No, there is an opportunity for you to check. When you are drawing from left to right, you always have an opportunity to check from right to left. Right? For example, if we start bending moment diagram from this side, okay, then also it should be like this only. So when, let us start. When you are on the right of the section, okay, when you are on the right of the section, downward should be taken as positive. I told you already, right? On the right of the section, downward should be taken positive. So m by l you will be drawing positive side and you will proceed because nothing else, no other load is there in between, right? So you can again get plus m by l only. So this is a check whether you have done correctly or not. You can always check. There is an opportunity. There is an advantage of shear force bending moment diagram is that you can always verify your solution. If you are drawn from left to right, you can verify from right to left. Both should be similar. Next one, bending moment diagram, right? As we mentioned earlier, unless there is any couples acting at the simple supports, there is no question of bending moment at a hinge or roller. So here there are no couples at the ends. So 2 points you can always put 0. 0 here and 0 here. Remember, the exception is only when you have couples acting directly on the supports. Then only you will get some moment here. Otherwise, when you find a roller or hinge, put it all without any no doubt. You can put 0 magnitude there when you are constructing your bending moment diagram. Next, here this ordinate is over. Now look at the, if you want to know the central ordinate, just find the area of this diagram. Okay, so up to this particular point, say a, this point distance was represented a, right? Up to this point I can find out. So let's say this point is a. At this point let us find out. So m by l, right? This is area I have to find. That's what I told. Shear force area will give you your direct value. M by l times a, right? So this ordinate is ma by l. Next, ma by l, right? That is our first ordinate. Next, at this point, what is happening? There is another moment entering. Okay, so ma by l, if you want to, this is when you are on the left of this particular load. So as soon as you enter this load, right, you are getting another bending moment here, right? So ma by l, and this is going to be, this is causing what kind of, why you have taken this positive actually? We have drawn on the upside. Why positive? Because and the left of the section clockwise moments are, this is causing a clockwise moment, is upward reaction, right? M by L is an upward reaction causing a clockwise couple. Okay, that's why it is positive. Now M for is what kind of moment it is causing? Anti-clockwise, so this should be negative. So Ma by L minus M going to be MB by L, minus MB by L. So that is the ordinate you will be getting on the downside. Okay, suppose one doesn't follow this particular point, what you do is you can start now from this side. Here also you just find the area of this. Okay, so what you will be getting? 0 anyway here. Here M by L times B you will be getting the area of this diagram, right? Earlier you found this area up to the point A. Now you find the area of this one. Okay, so this is going to be, this is spreading over a distance of B and this is spreading over a distance of A. So this becomes m by L times B. So MB by L. But what is the direction? Direction is going this way. That means this kind of direction. So this kind of direction is to be taken negative. Therefore, you should draw on the downside with an ordinate of ME by L. Right? Then how to join? Right? So when the shear force, I told you already in the beginning slides that when there is a couple, the variation of this particular uh, bending moment diagram is going to be either a sudden jump happens when there is a moment, otherwise it's going constantly. Okay, constantly increasing or constantly decreasing. So this way it will happen. So join by a linear line on both either side. 0 here, MA by here, L and MB by L here. Okay, that's all. This is your bending moment diagram. So if you draw exactly onto the scale, that's how it look like. Okay, this is the how when you draw exactly to the scale, right? M by L plus same thing and minus M by L, and this is going to be a triangular variation. And finally, if now we'll try to draw the shear force and bending moment diagram for the simply supported beam when it is subjected to triangular load. Okay, the triangular load has a intensity 0 at both the left and right ends, and having a maximum intensity W kilonewton per meter, okay, at the center. For this kind of loading, we will try to construct the shear force and bending moment diagram using the concept of uh, relations between the loading as well as shear force, loading shear force as well as shear force and bending moment relationships, which we have discussed, right? So in this process, the first requirement is you have to find the support reactions. So I am not getting much detailing on the determination of support reactions, right, which we have already discussed in a separate session. So we can refer to that. The essence of that particular finding the support reactions is simply apply the equilibrium conditions, right? Particularly sigma mz equal to 0 at any one of the supports and sigma fy equal to 0. With the help of these two equations, you can find out any support reactions you are desiring. Sigma fy equal to 0 and sigma mz equal to 0. These two equations you can apply to find the support reactions. In this case, of course, the loading is symmetrical. You don't have to endeavor much. It is a symmetrical loading. So what is the total load acting? That is nothing but your area of the diagram. If you convert this uniformly varying load into a point load, the total load acting on this particular beam is half. It is in the form of a triangle. So half times area of the triangle, half into base into height. Base is L, height is W. So WL by 2 is the total loading. So when it is symmetrically acting, the load will be distributed equally to both supports. So the reaction on this support is WL by 4 on this support and WL by 4 on the other right side support. Okay, both are upwards. So these are the reactions. So once you got the reactions, now we move on to the next step. Now you can start drawing the shear force diagram using the relationship between loading and the shear force. Okay, so for that, as we told, first thing is we should start with the sign convention. As the sign convention says, when you are on the left of the section, if you are having upward reactions, then you take them positive. Draw on the positive side, that is on the upper side. So as we mentioned previously, whenever you want to draw the shear force, minimally you have to take 3 points, right? Or bending moment, you take minimally 3 points. So select convenient points. Say one point on this end, another point somewhere here on the other end, and the third point somewhere at the middle. Okay, third middle or any desired point depending upon our requirement. Okay. So we have selected the 3 points. So first point we can start from this, and this is acting upwards. So if following the sign convention, your ordinate here will be WL by 4. So you can mark an ordinate of magnitude WL by 4 with a positive sign. Okay, WL by 4 is this particular quantity. So you got that WL by 4, right? This quantity is WL by 4. Okay. Next, on the other side, you can it is convenience with the shear force bending moment. You can draw from any side. Okay. So from this end also I can mark this ordinate WL by 4 on this side. This is acting upwards. So on the right of when you are on the right of the section, upward type of forces should be taken negative. So your ordinate is going to be negative there, and that is minus WL by 4. You mark that WL by 4. Okay. So here is a positive value, here is a negative value, right? So somewhere it's going to be negative. We do not know what is the distance. If you want, we can find out that, but at this point we can know minimally that there is a point. It may not be at the middle, we do not know, right? It may not be the middle point, but somewhere it's going to be 0. Let's take this point somewhere is going to be no yeah, it is a symmetric loading. It will be definitely at the center. If it is not symmetric, it will not happen at the center, but somewhere. Okay, if in this case it is going to be happen at the center because loading is symmetrical, and these ordinates also you see minus WL by 4 plus WL by 4. So you can simply join it. But joining is by what kind of relationship it is varying. We told in the beginning table that, right, what in the table I showed, right, when the loading is uniformly varying load, right, the shear force, okay, varies in a quadratic fashion, second order kind of parabolic curve. So it should be a parabolic. You join all the 3 points ordinates with a parabolic curve. So from here to here you join a parabola, and then from here to here join a parabola like this. This is going to be your shear force diagram. Alright. Then go to the next one, bending moment diagram. So this distance also we know now, right? L by 2. This is L by 2. This is L by 2. As we told, because this is because we have a symmetric load. Now bending moment diagram is very simple for simply supported beam, because two ordinates you know at point 1, that means at both ends, this one and this one. You see, is there any couple here? As we mentioned earlier, when there are no couples, simple supports always carry 0 moment. So two ordinates you know. So if at middle point, if you know, your diagram is completed. So how to know the middle ordinate? Use the relationship again, the relationship between shear force and bending moment. So if you want to know the shear force bending moment at this ordinate, say at the middle, the difference of the bending moment ordinate values will be coming from the area of the shear force diagram. So the area of this diagram is, if you found out, your ordinate will come. So what is the area of this particular diagram? It is a parabolic curve. So this parabolic area is, so if you inscribe this parabola in a rectangle, it occupies 2/3 of the rectangular area. So rectangular area of this one will be how much? This base in this length into breadth, right? So what you will be getting is L by 2 times, you can put small l or capital L, it doesn't make any difference, WL by 4. Okay. Now this is the rectangle area. In this, it occupies 2/3 of its area. So you can multiply 2 by 3. Right? So it's going to be how much? W, this is L, WL square by 12. So this is the ordinate you are going to get. So this is your WL square by 12. Okay, so join it. Now when you are joining, it should be with a cubic parabola. As already it is a quadratic variation, this is going to be a cubic variation. Right? This is the bending moment diagram. So that's all. When there is a triangular load symmetrically acting like this, this is the shape and this is your SFD. So if you want to see exactly onto the scale, this is how it look like. Right? This is how it look like. And the WL square. Okay. Now if you are having a triangular load like this, left end is say 0 and right end is having some intensity say W. So in this particular situation, how to draw the shear force and bending moment diagram? See, the loading can be even reverted like W magnitude here and 0 magnitude here. Then also the procedure remains unaltered. As it is, we can proceed. Okay, so let us go forward now. If you look at here, the first one, we are having the support reactions. Here is the first step, right? So as I mentioned, you simply apply the equilibrium equations, namely sigma mz and sigma fy equals 0. These two equations will help us to find the support reactions. Okay, so you will be getting, I am not dwelling on that because previously you have spent a lot of time on that, so you can refer to that particular discussion on finding the support reaction simply supported beam for various kinds of loadings, right? So you can refer to that. So you will be getting the support reactions now. So we are WL by 6 one side and WL by 3 on the other side. So you got the support reactions. Now let us start. Now follow the sign convention. So for constructing the shear force diagram, you at least take minimum 3 points as mentioned earlier. So first point here, second point here, and third point at our convenience, wherever no we are interested, somewhere you can take any third point. Okay, so taking that at first point, you already having some kind of vertical component here, you represent that. So that component is say WL by 6, right? So let us mark that ordinate WL by 6. So this is plus. Why plus? Because when you are moving, when you are on the left section, you are moving left to right, right? So that means you are on the left of the section. Your upward force, this is you are taking an upward force and moving towards the right, right? So in this case you have to take this as positive. So this is going to be plus WL by 6. Okay, then you mark the coordinate in the other side also. This also you know, no, when you are moving from right to left. Okay, that means you are on the right of the section. At the right of the section, the upwards is negative, right? So you mark this as a negative and the component value is minus WL by 3. Okay, so this component is WL by 3. Okay, WL by 3. Okay, now it's moving from positive to negative. That means minimally we can understand there must be 0 somewhere, right? So at some point it's going to be 0. So we are going to select that particular point as 3, right? So now you can join that. Of course we can find where it's going to be 0, we will find that, right? Before that itself we can construct the shear force diagram. So join this. So when we, what kind of relationship, through line or through constant way? Which way you have to join? Going to join? You are going to join through a quadratic curve. We mentioned right in the beginning, when there is a uniformly varying load, because based on the relationship between loading and shear force, it's going to be vary quadratically. So second order curve you can join, it's going to be like this. Okay, this is your SFD diagram, shear force diagram. Now one may be interested, where is this particular shear force is going to be 0. So for that what you have to do is, we already know this ordinate. So at some x distance it's going to be, say some x distance is going to be 0. X can be anywhere. I do not know where it is beginning, but some x distance is going to be 0. So what is the ordinate of the load value at this particular section x? Already we know at a distance L the intensity of the load is W. At x distance what is the intensity of the load? This load intensity will be W. At a distance of L, load is W. At a distance of X, it's going to be Wx by L. No, from the similar triangles also you can find, right? So it is simply proportionate. At L distance, load is W. At X distance, it is Wx by L. Now you find the area of this particular sector of X distance. So what is that? Half times, I am finding the area of this part from here to here in this X region. Okay, that's going to be half times base into height. Base is X, height is Wx square by X by L. So effectively it becomes Wx square by 2L. So now you can equate that WL by 6. I want to know where is the total shear force becoming 0, right? So WL by 6 minus Wx square by 2L. So if you solve this simple equation, right, you are going to get x equal to L by root 3. That's what you are going to get. So L by root 3, this distance from here to here is, L by root 3. Of course, if numerically if you want to calculate, it comes around some 0.577, around that. Okay, that is the distance. So you completed your shear force diagram. Now you move on to the bending moment diagram. So in bending moment diagram, always you know the value of the bending moment in simply supported at both ends, right? Is there any couple at any ends? There is no couple here, there is no couple here, there is no moment, right? So put 0 here. At roller support, at hinged support, always bending moment is 0. So put 0. So if one, as we told, minimally we are taking 3 points. So one more point, if you know, you can construct it. So let's say that point is going to be this one, right? We also mentioned during the relationship between shear force and bending moment, wherever shear force is becoming 0, there is the possibility of getting maximum bending moment. So this ordinate that is going to get is the maximum value. Okay, how much is that, right? You find the area of this, because the other ordinate, if you, the relationship says between shear force and bending moment, if you want to know the ordinate difference between the change in the bending moment between 2 points is nothing but the area of the bending moment diagram. Here one value is already 0, so simply find the area of this, then you got this ordinate, right? What is the area of this? As we told, this particular area, okay, is going to be 2/3 of the rectangular area. This is a parabolic curve. So 2/3 of this area is how much? This area, if I want 2/3 of WL by 6 times L by root 3. Okay, so if we simplify that, L by root 3, we simplify that, so you will be getting WL square by 3 times, right? 2 goes 3 times here, so 9 root 3. So you can write this ordinate as WL square by 9 root 3. That's it. Join it. You got all the 3 points with you. But what kind of curve you have to use? As we mentioned earlier, It is not a linear relationship, it is not a parabolic, but it is a quadratic, cubic variation, right? So join with a cubic curve. Finish. That is your MD. So using this relationship, you can simply draw even if the loading is very complicated. Okay. So of course all these are basic loadings that we are using, right? So exactly when you are trying to look at on the to the scale how to draw, this is the diagram. You can have a look at it. The same values, right? Plotted on to the exact scale. So WL by 6, WL by 3, and WL square by 9 root 3. This is a quadratic curve, and this is a cubic curve. Okay, so that's the way of constructing the shear force diagram for uniformly varying loads and triangular loads, right? Thank you.